Time began with a single cosmic heartbeat. This is the story of the universe learning to count, a journey from the frantic vibrations of atoms to the slow, grand tick of expanding space itself. By the end, you will understand the secret language the cosmos uses to measure its own existence. We will uncover how a dying star's pulse can keep perfect time, and why the empty void of space might hold the ultimate clock. What does it feel like to listen to the rhythm of reality? Our earliest ancestors measured time by watching the sky. They saw the sun's dependable arc from dawn to dusk, defining the day. They witnessed the moon's patient cycle from slender crescent to full luminous orb, marking a month. They tracked the slow parade of constellations, their return signaling another year. This was humanity's first clock, its face painted across the heavens. In ancient Babylon, meticulous records of planetary movements were kept on clay tablets. In Egypt, the annual flooding of the Nile coincided precisely with the rise of the star Sirius, creating a celestial alarm clock that dictated the agricultural cycle. These cultures were not just observing, they were learning to listen to the rhythm of the cosmos, translating its grand motions into the practical language of calendars and seasons. This primal connection reveals a profound truth. The universe was always a timekeeper, and we were simply its first students. We internalized the cosmic pulse, building our societies around its steady beat. Every modern clock, no matter how advanced, traces its lineage back to that fundamental relationship, to the moment we first looked up and saw order in the celestial dance. Then came the gears. In the monasteries and town squares of medieval Europe, humanity's relationship with time underwent a profound transformation. We moved from simply observing the heavens to building our own miniature universes of ticking metal. These intricate machines, powered by weights and regulated by escapements, were a declaration of independence from the sky. No longer were we solely dependent on the sun's shadow or the moon's phase. We had captured a slice of time's rhythm and enclosed it in a box. The true revolution arrived with the pendulum. When the Dutch scientist Christian Huygens designed the first pendulum clock in the 17th century, he harnessed one of Earth's most fundamental forces, gravity, to create a new kind of heartbeat. The swing of a pendulum is beautifully predictable, its period dictated almost entirely by its length. This regularity introduced a level of precision that sundials and water clocks could never dream of. Seconds could now be measured with stunning consistency, minutes counted with unwavering accuracy. This was the moment timekeeping truly became an engineering discipline. Yet for all its brilliance, the pendulum clock remained tethered to our world. Its steady beat was a direct consequence of Earth's gravitational pull. A pendulum swings differently at the top of a mountain than it does at sea level, and it is utterly useless in the weightlessness of space. So, while we had decoupled time from the stars, we had merely chained it to another cosmic constant. The pendulum's majestic swing was a precursor, a practice run for the far more precise oscillations to come. It proved we could find a regular, repeating phenomenon in nature and build a machine around it. The next step in our quest would require us to look not at swinging weights, but deep into the heart of matter itself, to the frantic, perfect vibrations of atoms. The steady swing of the pendulum was a marvel of our world, but the next leap in timekeeping required us to abandon the clockwork of the macroscopic and descend into the quantum realm. Here, in the invisible world of atoms, scientists found a rhythm of unimaginable perfection. They discovered that atoms like cesium-133 are not static. Their electrons dance between distinct energy levels, and with each quantum jump, they emit a whisper of electromagnetic radiation at a frequency so stable it defies belief. This was not a rhythm we built. It was a rhythm we discovered, a pulse written into the very identity of matter. Harnessing this phenomenon led to the first atomic clocks in the mid-20th century, a revolution so profound it changed the definition of time itself. In 1967, the world officially abandoned the astronomical second, which was tied to the erratic spin of our planet. Instead, we adopted a new universal standard. 1 second was officially defined as exactly 9,192,631,770 cycles of that radiation emitted by a cesium atom. This is not an approximation, it is a count. Think of the cesium atom as a microscopic tuning fork that vibrates over 9 billion times a single second. This incredible stability means an atomic clock will not gain or lose a second for millions of years. Its precision stems from the fact that the laws of quantum physics are the same everywhere. A cesium atom here on Earth is identical to one in a distant galaxy, making it a perfect universal oscillator. This quantum heartbeat now underpins our modern world. The entire global positioning system, for instance, would be useless without it. The satellites overhead contain atomic clocks, and the breathtaking accuracy of their time signals is what allows your phone to triangulate your position on the Earth's surface to within a few meters. Global financial networks, the internet, and communication grids all synchronized to this atomic metronome. We have literally tied our civilization to the vibration of atoms. This was the monumental shift, moving our measurement of time from the motions of planets to the fundamental vibrations of particles themselves. We are no longer just listening to the cosmos. We are reading its most basic operating manual, yet even this phenomenal precision is not the final word in time. The very fabric of space itself may hold a clock that makes the atomic tick seem crude by comparison. But the quantum heartbeat of atoms was not the only rhythm waiting in the cosmos. The universe had already built its own metronomes, and we found them by accident. In 1967, a radio telescope detected a strange, repeating signal. A pulse so perfectly regular that astronomers briefly entertained the possibility it was a beacon from an alien civilization. They named the source LGM1 for Little Green Men. The truth was both more natural and far more extraordinary. They had discovered the first pulsar, a rapidly spinning neutron star. A neutron star is the incredibly dense corpse of a massive star that has exploded in a supernova, squeezing more than the sun's mass into a sphere just a few miles across. A single teaspoon of its material would weigh billions of tons. As this stellar remnant spins, it acts like a cosmic lighthouse. Beams of intense radiation shoot out from its magnetic poles, and if those beams sweep across Earth, we see a flash with every rotation. This is the pulsar's pulse. The regularity of this flash is breathtaking. Some pulsars spin hundreds of times per second, their periods stable to a level that rivals our best atomic clocks. Here was a natural timekeeper, a clock the size of a city, ticking with the precision of a quantum oscillator, and it was built by the violent death of a star. These celestial lighthouses are now scattered across the galaxy, each one a unique chronometer in the sky. Scientists use their impeccable rhythm to conduct incredible experiments. By monitoring the subtle changes in the arrival times of pulses from an array of pulsars, astronomers can listen for the faint background hum of gravitational waves, ripples in spacetime itself caused by colossal events like merging supermassive black holes. This is a galactic-scale observatory with pulsars as its detectors. Their pulsars have even been proposed as a navigation system for future interstellar travel, a cosmic GPS that would guide ships between the stars. Pulsars are a powerful reminder that the universe is not just full of time, it is actively keeping time. The same physical laws that govern a swinging pendulum on Earth also govern the spin of a stellar corpse light years away. This intricate cosmic clockwork shows us that temporality is woven into the very fabric of matter and space. Yet, even the steady tick of a pulsar is subject to the grandest rhythm of all, the slow, relentless expansion of the universe itself. The pulsar's steady rhythm is anchored in the gravity of its own dense corpse, but the stage upon which it performs is stretching. In the 1920s, Edwin Hubble made a staggering discovery that redefined our cosmic context. By observing the faint light from distant galaxies, he found that nearly all of them are moving away from us. More profoundly, the farther away a galaxy is, the faster it appears to be receding. This was not a random flight, it was a pattern, a clear sign that the very fabric of space itself is expanding. The entire universe is growing. This relationship between a galaxy's distance and its speed of recession is encapsulated in a single, crucial number, the Hubble constant. It is the expansion rate of the universe. Think of the cosmos as a loaf of raisin bread rising in an oven. As the dough expands, every raisin moves away from every other raisin. A raisin that was initially twice as far away will appear to move twice as fast. The Hubble constant tells us how fast that cosmic dough is rising. This number does more than just describe the present. It acts as a clock that lets us rewind the film of creation. By measuring how fast the universe is expanding now, we can calculate backwards to the moment when all matter and energy were compressed into a single point, the Big Bang. This is how we arrive at the universe's age, an estimated 13.8 billion years. Our most precise measurements of this cosmic speed limit come from powerful tools like the Hubble Space Telescope, which painstakingly measures the distances to other galaxies, and the Planck satellite, which studied the faint afterglow of the Big Bang itself. Yet a profound mystery persists. These two gold standard methods yield slightly different values for the Hubble constant. It is as if two of the most accurate clocks ever built are ticking at irreconcilable rates. This discrepancy hints that our understanding of the universe is incomplete, that there may be unknown forces or particles influencing the expansion. The Hubble constant is the universe's master tempo, a slow, deep tick that measures the growth of space on the grandest scale, but this rhythm is not constant forever. The cosmic clock is itself changing, accelerating under the influence of a mysterious dark energy, a force that is stretching the very meaning of time. This acceleration revealed a force opposing gravity itself, a repulsive energy woven into the vacuum of space. We call it dark energy, and it is the dominant component of our universe, making up about 68% of all that exists. For decades, the prevailing assumption was that the universe's expansion, set in motion by the Big Bang, was gradually slowing down due to the collective gravity of all matter pulling everything inward. The discovery of acceleration turned that model on its head. It was as if we had thrown a ball into the air, expecting it to fall back, only to watch it fly faster and faster into the sky, pushed by an unseen hand. This invisible driver introduces a profound new framework for cosmic time. If the universe's expansion is accelerating, then the very rate at which cosmic time unfolds is also changing. The universe's clock is not just ticking, it is ticking faster as the eons pass. This challenges our most fundamental intuition about time as a uniform, constant river flowing at the same speed for everyone, everywhere. On the grandest scales, time itself appears to be evolving in concert with the cosmos. The influence of dark energy means that the future of cosmic timekeeping is one of increasing isolation. As the expansion accelerates, galaxies beyond our local group will eventually be pushed away so fast that their light can never reach us. The cosmic microwave background, the faint echo of the Big Bang, will redshift into oblivion. For any future civilization in our galaxy, the universe will appear as a lonely island of stars in an endless, dark, and ever-quietening void. There will be no distant supernova to observe, no new galaxies to discover. The evidence for the Big Bang itself will have faded away, and with it, the ability to measure the universe's age or expansion history. This dark energy-dominated era forces us to confront the ultimate fate of time. Will this acceleration continue forever, tearing apart all structures until even atoms are ripped asunder in a final big rip? Or will dark energy's influence change, leading to a different destiny? To answer these questions, we must look back to the very beginning, to the moment the cosmic clock started ticking. The story of time does not begin with the steady expansion we see today, but with an event so violent and rapid it challenges the limits of physics itself. That moment of infinite density, the singularity we call the Big Bang, was not just the beginning of space and matter, but the very birth of time itself. Before that event, the concepts of before and after had no meaning. There was no clock, no rhythm, no past. Then, in an incomprehensible flash, the universe erupted from a point of infinite heat and density, and the cosmic clock started its very first tick. This was time zero. As the newborn universe expanded and cooled at a ferocious rate, it was a seething soup of fundamental particles and energy, too hot for light to travel freely. For nearly 400,000 years, photons were trapped in a constant dance of creation and annihilation with electrons, making the cosmos an opaque, glowing fog. Then, in a pivotal moment, the universe cooled enough for atoms to form. Suddenly, light was set free. That first flash of liberated light, now stretched and cooled by the relentless expansion of space for billions of years, reaches us today as a faint, cold whisper from the past. We call it the cosmic microwave background. This discovery was one of the greatest accidents in scientific history. In 1965, two radio astronomers, Arno Penzias and Robert Wilson, were troubleshooting a persistent, maddening hiss in their giant horn antenna. They scrubbed away pigeon droppings and checked every connection, but the noise remained, a uniform static coming from every direction in the sky. They had not found an equipment flaw. They had stumbled upon the afterglow of creation itself, the cooled remnant of the universe's fiery birth. This cosmic microwave background is the oldest light we can see, a snapshot of the infant cosmos when it was a mere 380,000 years old. It is not a picture of the Big Bang, but a baby picture of the universe, taken the moment it became transparent. This faint glow is the ultimate time capsule, and its temperature is not perfectly uniform. When we map it with exquisitely sensitive instruments on satellites like COBE, WMAP, and Planck, we see tiny fluctuations, ripples of slightly warmer and cooler patches. These imperfections are the cosmic seeds, the gravitational blueprints for everything that would follow. The slightly denser regions would, over eons, pull in more matter, eventually growing into the vast cosmic web of galaxies and galaxy clusters we see today. By reading these subtle temperature variations, cosmologists can calculate the universe's age with stunning precision, confirm its flat geometry, and inventory its contents, confirming the presence of both dark matter and dark energy. This primordial radiation is the foundational clock that calibrates our entire cosmic timeline, a direct line to the universe's first moments. Yet, this profound connection to the dawn of time raises an even deeper question. a question that pushes at the very boundaries of physics. If the Big Bang was the beginning of time, what, if anything, could have come before? The cosmic microwave background gives us a picture of the universe's infancy, but it cannot show us what happened in its very first moments, or if there was a before at all. Our most successful model for those initial instants is cosmic inflation. This theory proposes that a fraction of a second after the Big Bang, the universe underwent a growth spurt of unimaginable speed, expanding exponentially faster than the speed of light. In less time than it takes to blink, a subatomic speck of space was stretched to a size larger than our entire observable universe today. This violent inflation would have ironed out any wrinkles, explaining why the cosmos appears so flat and uniform on large scales. Yet, this very process may have erased any trace of what came before. It is like blowing up a balloon that has a complex pattern drawn on it, only to inflate it so rapidly that the pattern is stretched into a featureless, smooth surface. We are left with a universe that appears to have a definite beginning, but the inflationary model opens the door to a far stranger possibility. What if inflation is not a one-time event, but a perpetual engine? In this eternal inflation scenario, our entire cosmos is just one bubble in a frothing, infinite multiverse. While our bubble stopped inflating, giving rise to the stars and galaxies we see, the greater meta-universe continues to expand exponentially forever, constantly giving birth to new bubble universes, each with its own unique laws of physics. In this view, the Big Bang was not the absolute beginning of time, but merely the moment our local cosmic environment was born. Time, in the wider multiverse, may have no beginning and no end. Another profound challenge to a singular beginning comes from cyclic models. These theories imagine a cosmos without start or finish, an endless cosmic heartbeat. In one version, our universe expands until dark energy wanes, then gravity pulls everything back together in a cataclysmic big crunch. But instead of collapsing into a singularity and ending, this collapse triggers a rebound, a new Big Bang that births a fresh universe from the ashes of the old. In this model, time is cyclical, resetting with each new cycle, though the laws of physics may carry over, allowing for a form of cosmic memory. It is a universe that has always been and will always be, breathing in and out across eons. These ideas force us to confront the limits of our language and intuition. Asking what happened before the Big Bang might be as meaningless as asking what is north of the North Pole. If time itself began with our universe, then there simply is no before. Yet, if our universe is part of a vaster, timeless multiverse, then our cosmic clock is merely a local phenomenon, one ticker in an infinite sea of time. This exploration pushes physics into the realm of philosophy, questioning whether time is a fundamental property of reality or merely an emergent illusion, a side effect of the universe's increasing disorder. Our entire experience of time's arrow, from memory to causality, might be a direct consequence of our universe's specific and finely tuned initial conditions. This leads us to the most critical question of all. Why do the fundamental constants that govern reality have the exact values they do? If they were even slightly different, time as we know it would not exist, and neither would we. These fundamental constants are the universe's ultimate operating system. Think of them as the unchangeable settings, the cosmic code that dictates how reality behaves. Without them, time would have no consistent meaning. The speed of light in a vacuum, for instance, is not just a speed limit. It is a fundamental conversion factor between space and time, weaving them into a single fabric called space-time. Planck's constant governs the quantum world, dictating the energy of a photon and setting the scale for the frantic vibrations inside an atomic clock. The gravitational constant determines the strength of gravity's pull, shaping the orbits of planets and the warping of space-time around massive stars. These numbers are not just measured, they are the bedrock of physics itself. Their constancy is what allows a second measured by a cesium atom in a lab on Earth to be the exact same duration as a second defined by the spin of a pulsar 1,000 light-years away. This universal reliability is the reason we can trust our clocks, build a GPS network, and confidently project our models back to the first moments of the Big Bang. We assume, because all evidence supports it, that the laws of physics and these constants are the same everywhere. This principle of uniformity is what makes cosmology possible. It allows us to look at the light from a galaxy 10 billion light-years away and understand the processes that created it, because the same rules applied there and then as apply here and now. Could these constants have been different in the past, or might they change in the future? Some theories have suggested that the fine structure constant, which governs the strength of electromagnetic interactions, might have varied slightly over cosmic history. Scientists have tested this by analyzing the light from incredibly distant quasars, looking for subtle shifts in the absorption lines of ancient clouds of gas. The cosmic microwave background provides another stringent test. So far, the results are clear. The constants appear to be truly constant. They are the fixed pillars in an evolving cosmos, the unwavering rules that allow the cosmic clock to function. This reliability, however, faces its ultimate test in the most extreme environments the universe can offer. Near a black hole where gravity becomes so intense that not even light can escape, the very flow of time is stretched and distorted in ways that challenge our deepest intuitions. The unwavering constancy of physical laws faces its ultimate trial at the edge of a black hole. Here, gravity ceases to be a simple force and becomes a profound distortion of the cosmos's fabric. Einstein's theory of general relativity revealed that massive objects do not merely pull on things, they warp the very space-time around them. Think of space-time as a taut, flexible rubber sheet. A star creates a gentle dip in this sheet, guiding planets to orbit around it like marbles rolling in a bowl. A black hole, however, is so immensely heavy and dense that it punches a hole through the sheet, creating a gravitational pit so deep that not even light can climb out. This warping has a startling consequence for time itself, an effect called gravitational time dilation. The closer you get to this immense gravitational well, the slower time flows relative to an observer far away. At the black hole's boundary, the event horizon, time from an outside perspective appears to grind to a complete halt. A clock falling toward that horizon would seem to tick slower and slower, its light reddening and dimming until it freezes completely, forever etched on the edge of oblivion. Yet, for the astronaut unfortunate enough to be falling in, their own clock would tick forward at a normal rate. They would experience nothing strange as they crossed the event horizon, but their entire future, from our perspective, would be compressed into that single, frozen moment. This is not a theoretical illusion, it is a fundamental feature of reality. We have measured this effect right here on Earth. Atomic clocks placed at higher altitudes, farther from Earth's gravitational pull, run measurably faster than identical clocks at sea level. Your head is literally aging faster than your feet, though by an infinitesimally small amount. On a cosmic scale, we observe this with the star S2 as it makes its closest approach to the supermassive black hole at the center of our galaxy. The light from the star redshifts as it dives through the intense gravity, its clocks slowing down exactly as Einstein predicted. This relativity shatters the Newtonian idea of a single, universal clock ticking the same for everyone. Time is personal. Your experience of it depends entirely on your local environment, on your speed, and your gravitational circumstances. This means that for a civilization attempting to build a perfect cosmic clock, a single time standard for the entire universe is impossible. Every planet, every star, every spaceship moving at a different speed or sitting at a different gravitational potential has its own valid but different time. The cosmic clock is not one metronome but a symphony of countless individual ticks, each playing at its own tempo. This relativistic truth forces us to ask what time really is, if it can be so fluid and personal. Is it merely a side effect of a deeper, more fundamental structure, an emergent property of a universe built from something even more strange? Einstein's prediction of gravitational waves was a final, elegant piece in his theory of gravity, but for a century they remained elusive. Then, in 2015, the LIGO Observatory felt it, a tremor in reality so faint it had to be teased from noise smaller than a proton. Two black holes, each about 30 times the mass of our Sun, had spiraled into each other over 1 billion light-years away. In their final, frantic dance, they churned the fabric of spacetime itself, sending out ripples that traveled at the speed of light for eons before washing over Earth. That first detection was not just a confirmation of a theory, it was the opening of a new sense. We had learned to feel the vibrations of the cosmos. These gravitational waves are not like sound or light. They are literal stretches and squeezes of space. As a wave passes through you, you would very slightly elongate in one direction and compress in the perpendicular direction before the pattern reverses. The effect is unimaginably tiny, which is why detecting it required some of the most precise instruments ever built, but the information they carry is monumental. The specific waveform of a gravitational wave, its rising chirp and final ring down, is a perfect cosmic stopwatch. It encodes the precise masses of the colliding objects, their orbital dynamics, and the exact moment of their merger. By reading this signal, scientists can measure the event's distance and duration with incredible accuracy, independent of the light it may or may not produce. This makes gravitational waves a new kind of clock, one that ticks not with atomic vibrations, but with the shudder of spacetime itself. This new sense fully came of age in 2017, when a different kind of collision occurred. Two neutron stars spiraled together, and this time, as they merged, they erupted in a blaze of light across the entire electromagnetic spectrum. Gravitational wave observatories felt the ripples, and telescopes around the world and in space saw the flash. This was multi-messenger astronomy in action, the ability to both hear and see the same cosmic event. The gravitational wave signal provided the precise timeline of the merger, while the light allowed astronomers to identify the host galaxy and measure its distance through traditional methods. This powerful combination offers a new way to measure the universe's expansion rate, providing a fresh, independent check on the Hubble constant. By comparing the distance measured from the gravitational wave signal with the redshift of the host galaxy, we can calibrate the cosmic yardstick itself. Each new gravitational wave detection is a direct probe of the most extreme gravity in the universe, a test of whether Einstein's theory holds true in the violent crucible of a black hole merger. These ripples are messengers from the edge of spacetime, carrying a pure, unadulterated record of time itself, shaped by gravity alone. They reveal a universe where time is not just measured, but actively molded by the most powerful events in creation. The ultimate fate of time is written in the universe's expansion rate and its mysterious composition. Cosmologists have mapped out several distinct endings, each with profound implications for the cosmic clock. The first and currently most favored scenario is known as the heat death. In this future, the universe continues to expand and accelerate forever, driven by dark energy. Galaxies drift apart beyond the cosmic horizon, stars burn out, and black holes slowly evaporate over unimaginable eons. Eventually, the universe reaches a state of maximum entropy, a final, uniform temperature just a fraction of a degree above absolute zero. In this state, no energy can be transferred, no work can be done, and no processes can occur. The universe becomes a thin, cold, and eternal sea of diluted particles. In this heat death, the progression of time, as we define it by change and causality, would effectively cease. There would be no before and after because nothing would ever happen again. The cosmic clock would not stop ticking because its battery died. It would stop because there was no longer any change left to measure. A second, more dramatic possibility is the Big Crunch. This scenario would require the density of the universe to be high enough that gravity eventually overcomes the push of dark energy. The expansion would slow, halt, and then reverse. Galaxies would begin rushing toward each other, space would contract, and the temperature and density of the cosmos would soar. In a mirror image of the Big Bang, everything would collapse back toward a singularity. In such a cataclysm, what would become of time? Some theoretical models suggest that in a closed, cyclic universe, time itself might reverse or simply reset, with the Big Crunch birthing a new Big Bang in an endless cosmic cycle. The clocks of one universe would be wiped clean, only to start anew in the next. The most violent end is the Big Rip. If the repulsive force of dark energy were to strengthen over time, it would not just push galaxies apart, it would eventually overcome all other forces. First, galaxy clusters would be torn apart, then individual galaxies. As the acceleration becomes infinite, stars are ripped from their systems, planets from their stars, and finally, atoms are shredded apart. Space-time itself would be torn asunder. In this scenario, time does not gradually become meaningless. It meets a definitive, abrupt end the moment the fabric of reality is destroyed. While current evidence makes the heat death the most likely outcome, these possibilities force a fundamental question. Does time, which seemingly began with our universe, also have an end? The answer depends entirely on which of these cosmic destinies awaits us. This grand speculation about the ultimate future of time brings us back to our own world, to the quiet hum of the devices in our pockets. The same cosmic principles that govern the fate of galaxies are harnessed to guide us home. That precise cosmic clockwork is not locked away in an observatory. It is in your pocket right now, guiding you through an unfamiliar city. Every time you use a GPS navigation app, you are relying on a network of atomic clocks orbiting high above the Earth. These satellites continuously broadcast signals that essentially say, here is my location, and here is the exact time according to my onboard atomic clock. Your phone receives these time-stamped signals from multiple satellites. Since the signals travel at the speed of light, even a microsecond error in timing translates to a positioning error of over 300 meters. To pinpoint your location within a few meters, the system requires nanosecond precision. But there is a cosmic complication. The satellites are moving at thousands of miles per hour and are in a weaker gravitational field than we are on the Earth's surface. Because of this, Einstein's theories of relativity come into play. The satellite's clocks run faster than identical clocks on the ground by about 38 microseconds per day. If this relativistic drift were left uncorrected, your GPS would accumulate errors of over 6 miles per day, rendering it utterly useless within minutes. So, engineers pre-adjust the clocks on the satellites before launch, deliberately slowing them down by that exact amount so that once in orbit, they tick in sync with clocks on Earth. Your driving directions are literally corrected for the warping of space-time. This synchronization extends far beyond navigation. The entire global financial system depends on it. High-frequency stock trades, which can occur in millionths of a second, must be time-stamped with absolute precision to determine their order and prevent chaos in the markets. Our power grids use synchronized time to detect the location of a fault, like a downed power line, by comparing the precise moment a disturbance appears at different monitoring stations. Even the internet relies on this coordinated time to manage data traffic and prevent digital gridlock. These are the invisible threads of universal time, woven directly into the fabric of our civilization. This reliance on hyper-precise time forces a profound question about its fundamental nature. Is the flow of time a smooth, continuous river as it appears in our daily lives? Or is it more like a movie, a series of incredibly rapid, discrete frames? Some theories of quantum gravity suggest that at the most fundamental level, at the Planck scale, time might not be continuous at all. It could be quantized, meaning there is a smallest possible unit of time, a single tick of the cosmic clock that cannot be divided further. This unit, the Planck time, is an almost incomprehensibly short 10 to the power of negative 43 seconds. If this is true, then the smooth passage of time is an illusion, a cascade of ultimate moments flickering by too fast for any clock to ever measure. Our most precise atomic clocks are now probing this frontier, seeking evidence that time itself has a granular structure. We have built our world upon the steady rhythm of the cosmos, only to discover that the very nature of that rhythm may be far stranger than we ever imagined. Our entire civilization runs on the illusion of a perfectly smooth, flowing river of time. But what if that river is actually a cascade of unimaginably tiny, discrete droplets? This is not just a philosophical puzzle. It is a frontier of physics that questions the very nature of reality. The classical view, inherited from Newton and Einstein, treats time as a continuous background, a smooth stage upon which the events of the universe play out. In this view, you could always divide a second into a smaller fraction, and then divide that fraction again, on and on forever, into infinity. But at the extreme scales where gravity and quantum mechanics collide, this beautiful continuity may shatter. Theories like loop quantum gravity propose that spacetime itself has a structure, a fabric woven from finite, indivisible loops. In this picture, time is not smooth. It is quantized, meaning it comes in the smallest possible packets. The fundamental unit is the Planck time, an interval so brief it defies human comprehension. It is 10 to the power of negative 43 seconds. To put that in perspective, a single second contains more Planck time units than there have been seconds since the Big Bang. If time is truly granular at this level, then the universe operates like a cosmic digital film, advancing frame by frame at a speed so phenomenal that the illusion of motion is flawless. This has a staggering implication. There is a fundamental limit to time measurement, a point beyond which no clock, no matter how advanced, can ever resolve a shorter duration. The cosmic clock would have a finite frame rate. So far, our most sensitive experiments, including the latest atomic clocks, have found no evidence of this granularity. Time to all our instruments appears perfectly smooth, but the search continues because finding that grain would be a revolution on par with the discovery of atoms. It would mean that our most fundamental experience of reality, the steady flow of time, is an emergent property of a deeper, digital-like structure. This concept forces us to reconsider time across human history as well. Different cultures have perceived time's flow in profoundly different ways. Some ancient civilizations saw time as a great circle, endlessly repeating. Others, like the Maya, developed astonishingly precise calendars that tracked vast cycles within cycles. The modern Western world largely views time as a linear arrow, a one-way street from past to future. an idea deeply influenced by the rise of mechanized clocks and the Industrial Revolution. Yet all these perceptions, from the cyclical to the linear, are built on the same underlying physical reality. Whether our minds interpret time as a wheel or a river, the question remains. Is the substrate of that experience a continuous stream or a breathtakingly rapid series of still images? Unifying the quantum world with the gravitational cosmos may require us to accept that time itself is born from something more fundamental, a reality where the familiar tick of the clock is merely the echo of a deeper, more discrete truth. The steady tick of a clock feels absolute, yet our human interpretation of its rhythm is anything but universal. Ancient Hindu scriptures describe immense, repeating cycles of creation and destruction, where universes breathe in and out over trillions of years. For the Maya, time was a sacred spiral of interlocking cycles, a complex calendar governing not just agriculture but the very fabric of spiritual reality. These cosmological views saw time as fundamentally cyclical, a wheel of eternal return. In stark contrast, the Abrahamic traditions of Judaism, Christianity, and Islam introduced a powerful linear arrow of time, a narrative of unique creation moving toward a final destiny. This linear perspective of a singular past and an open future would later provide a fertile philosophical ground for the scientific idea of cosmic evolution. The great philosophers then sharpened the debate. Aristotle argued time was a measure of change, a numbering of motion, and could not exist without events to mark its passage. Isaac Newton, however, declared time was absolute and mathematical, flowing at a constant rate independent of anything external, providing a universal stage for the laws of physics. Immanuel Kant went a step further, proposing that time is not an objective feature of the world at all, but a fundamental structure of the human mind, a lens through which we must perceive reality. Modern physics has sided, in a way, with Aristotle and against Newton. Einstein's relativity dethroned absolute time, showing it is relational, emerging from the interactions of objects and the geometry of spacetime. There is no single master clock for the universe, only a web of local times. This scientific revelation does not invalidate the cultural and philosophical views, but rather enriches them. It reveals that our quest to build a perfect cosmic clock is not just a technical challenge, it is the latest chapter in humanity's oldest and most profound conversation. We are trying to measure something that is simultaneously a physical reality, a cultural construct, and a deeply personal experience. The feeling of a slow, boring hour versus a fleeting moment of joy is a testament to time's psychological dimension, a layer of reality that no atomic clock can ever capture. This cultural and philosophical journey reminds us that every clock we have ever built, from the sundial to the atomic fountain, is not just a machine for measuring intervals. It is an expression of our place in the cosmos, a tool for finding meaning in the vast, unfolding story of existence. And now, that search for meaning is driving us to build clocks of such staggering precision that they promise to reveal entirely new layers of physical reality. The relentless pursuit of precision has now birthed clocks that make their cesium ancestors seem almost crude. In laboratories around the world, a new generation of timekeepers called optical lattice clocks is redefining accuracy. Where a cesium atomic clock might not lose a second in 100 million years, an optical lattice clock could, in theory, maintain perfect time for the entire current age of the universe, a span of over 13 billion years. This staggering leap is possible because these clocks do not use the microwave frequencies of cesium. Instead, they harness light, which oscillates at frequencies nearly 100,000 times higher. Think of it as moving from counting the slow, steady drips from a faucet to counting every single molecule in a rushing river. The core of this technology is the strontium atom. Scientists use a web of laser light, an optical lattice, to trap thousands of these atoms, holding them in perfect stillness. Another set of lasers cools them to a temperature just a whisper above absolute zero, slowing their motion to a near standstill. This incredible isolation shields the atoms from the tiny perturbations that would nudge a cesium clock out of sync, the minuscule jostles from magnetic fields, or even the ambient heat of the room. Suspended in this laser prison, the strontium atoms become near-perfect pendulums, their electrons dancing between energy levels with a rhythm of breathtaking purity. This phenomenal stability is not just for setting records. It opens a new window for testing the bedrock of physics itself. Scientists are now using these clocks to hunt for evidence that the fundamental constants of nature might not be so constant after all. Could the fine structure constant, which governs the strength of electromagnetic forces, be changing imperceptibly over time? By comparing two optical clocks based on different elements, researchers can look for a tiny drift in their relative ticking rates, a sign that the very rules of the game are shifting. These devices are so sensitive they could potentially detect the subtle influence of dark matter. A wisp of dark matter drifting through the laboratory might momentarily alter the properties of an atom, causing the clock's rhythm to stutter, leaving a faint fingerprint of the universe's most elusive substance. The ambition for these clocks extends far beyond Earth's surface. Projects are already underway to place atomic clocks in deep space or in orbit around other worlds. Imagine a network of these ultra-precise clocks distributed throughout the solar system, each one synchronizing to a common time standard. This solar system internet would enable spacecraft to navigate autonomously with centimeter-level accuracy, allowing for precise landings on distant moons and asteroids. Communication with rovers on Mars would become instantaneous, as their local time would be perfectly locked with clocks on Earth. This creates a framework for a truly interplanetary civilization, bound together by a shared, hyper-accurate perception of time. Yet this incredible precision forces a profound logistical challenge. How do you standardize time across the vast, relativistic distances of space? A clock on Mars, with its different gravity and orbital speed, will naturally tick at a slightly different rate than an identical clock on Earth. A clock on a fast-moving spacecraft will fall further out of sync. To create a functional solar system time, we would not be enforcing a single tick, but rather building a complex map of all these relative times, constantly calculating the corrections needed to translate between them. We are approaching a point where our ability to measure time is so exquisite that it reveals the fluid, personal nature of time itself, challenging us to build a clock that is not one device, but a symphony of interconnected rhythms spanning the void. This very challenge of synchronizing a solar system forces us to confront a cosmic truth. There is no master clock for the universe. Our dream of a single, cosmic coordinated universal time is shattered by Einstein's revelation that time is personal. A clock on Mars runs faster than one on Earth due to the red planet's weaker gravity. A probe traveling at a significant fraction of light speed would have its clock slow down relative to mission control. Near a black hole, time would crawl to a near standstill from our perspective. This means that for future astronauts traveling between worlds, their personal experience of time, their aging, and their shipboard clock will genuinely differ from the time experienced by those they left behind. This is not a technical error, it is a fundamental feature of reality. Simple synchronization is impossible because every location and every trajectory has its own valid time. The challenge then becomes not about enforcing a single tick, but about creating a cosmic time translation map. we would need a framework that constantly calculates the relative time difference between every planet, every moon, and every spacecraft in the solar system, accounting for their individual speeds and gravitational environments. This is the only way to coordinate a landing on Europa with a command sent from Earth, or to schedule a meeting between colonists on Mars and a passing interstellar freighter. Even our current system on Earth, Coordinated Universal Time, hints at this complexity with its leap seconds, which are added to account for the planet's infinitesimally slowing rotation. We are already making small, manual corrections to align our precise atomic time with the messy, real-world motion of our planet. Extending this to a galactic scale is a problem of unimaginable complexity. It would require a new physics-based protocol, a set of rules that seamlessly integrates the smooth, warped geometry of general relativity with the potential granularity of quantum time. This is not just an engineering puzzle, it is a fundamental requirement for any civilization that hopes to truly become interplanetary, let alone interstellar. Without a way to navigate this web of relative times, our conversations across the void would be a cacophony of mismatched clocks, and our ships would be lost in a sea of temporal confusion. The ultimate success of our cosmic journey hinges on learning to speak the universe's true, fluid language of time. This very challenge of synchronizing a solar system forces us to look beyond its boundaries toward the stars. The search for extraterrestrial intelligence is at its heart a search for a shared rhythm in the cosmos. If another civilization is out there, how would we even begin to converse across the light years? Any signal we receive would be a message from the deep past, and any reply we send would be a letter to the far future. This immense time delay means that communication would be less a conversation and more an exchange of time capsules, each one requiring a universal language to decode. That language might be time itself. Scientists involved in the search speculate that an advanced species would not send a simple hello. They would likely transmit a complex message built upon fundamental constants, using the universe's own clocks as a reference. The regular pulse of a pulsar, for instance, could serve as a cosmic metronome, a standard unit of time that any technological civilization could observe and understand. The message might be encoded in the timing between pulses, a binary code written not in ones and zeros, but in the silent intervals between ticks of this natural clock. Or it could be synchronized to the vibrational frequency of a hydrogen atom, the most common element in the universe, whose properties are the same everywhere. This would be a way of saying we both count time the same way, but would we, an alien biology might perceive the flow of time entirely differently. A species living on a world orbiting a pulsar, bathed in intense gravitational fields, could experience time dilation as a normal part of their daily existence. Their entire conception of past, present, and future could be alien to us. Their message might not be in the signal's content, but in its very structure, a rhythmic pattern that only makes sense if you understand their local experience of time. The synchronization of our clocks, both literal and conceptual, could be the first and most crucial step toward mutual understanding. It forces us to consider time not as a human invention, but as a cosmic scaffold, a universal framework upon which any two minds, no matter how different, could potentially build a common reality. This speculative bridge between worlds, built from the ticking of pulsars and the vibrations of atoms, is the ultimate testament to time's power as a unifying principle. It drives our own technological evolution, pushing us to build ever more precise clocks here on Earth, not just to navigate our own world, but to one day listen for a rhythm in the silence that matches our own. Deep beneath our feet, locked within the ancient rocks, lies a clock of a different kind. It does not tick with the swing of a pendulum or the vibration of an atom, but with the slow, inevitable decay of atomic nuclei. Elements like uranium-238 are inherently unstable. Over immense spans of time, they transform into lighter, more stable elements at a rate that is astonishingly predictable. This process, called radioactive decay, acts as a perfect geological chronometer. Each radioactive isotope has its own unique half-life, the time it takes for half of a sample to decay. For uranium-238, that half-life is about 4.5 billion years, nearly the entire age of our solar system. By measuring the ratio of the original parent element to the daughter product in a rock, geologists can calculate precisely how long ago that rock crystallized. This is how we know the oldest rocks on Earth are over 4 billion years old, and how we date the fossils of the earliest life forms. But this terrestrial clock has a cosmic origin story. The heavy elements necessary for radioactive decay were not forged in the Earth's infancy. They were born in the catastrophic explosions of distant, dying stars. A supernova is a cosmic alchemist, its unimaginable pressure and heat fusing lighter elements into heavy ones like uranium and thorium, then scattering them across the galaxy. Our solar system condensed from a cloud of gas and dust enriched by these ancient stellar explosions. The radioactive clocks that now tick within our planet are the lingering legacy of those cosmic events. This means the very tools we use to measure Earth's deep time were provided by the universe itself. Scientists perform a remarkable calibration, aligning the timelines written in our planet's rocks with the timelines of the cosmos. By dating meteorites, the leftover building blocks of the solar system, and comparing those ages to models of stellar evolution and galactic chemical enrichment, they synchronize Earth's geological calendar with the broader cosmic clock. This reveals a profound connection: the formation of our planet, the emergence of life, and the evolution of species are not isolated terrestrial affairs. They are chapters in a much larger story paced by universal rhythms. A more recent but equally profound link between cosmic time and our own history is radiocarbon dating. The nitrogen in our upper atmosphere is constantly bombarded by cosmic rays, high-energy particles originating from the sun and distant supernova. This collision creates a radioactive isotope of carbon, carbon-14. Plants absorb this carbon through photosynthesis, animals eat the plants, and so carbon-14 becomes incorporated into all living things. While an organism is alive, the amount of carbon-14 in its tissues remains in equilibrium with the atmosphere. But when it dies, the clock starts ticking. Carbon-14 decays with a half-life of about 5,730 years. By measuring the remaining radioactivity in an ancient piece of wood, a bone, or a cloth, archaeologists can determine when that organism died. This technique has allowed us to date everything from the linen of the Dead Sea Scrolls to the frozen remains of Ötzi the Iceman, precisely anchoring human history within a specific time frame. Yet, this method is itself a record of cosmic activity. Fluctuations in the sun's magnetic field, which modulates the cosmic rays reaching Earth, cause slight variations in the production of carbon-14 over centuries. By studying the rings of ancient trees which provide an annual record of these fluctuations, scientists can correct the radiocarbon clock, making it even more precise. Our planet is a layered archive, a time capsule preserving eons of events. Each stratum of sedimentary rock is a page in a history book, while the radioactive isotopes within them are the precise dates written in the margins. The iridium-rich layer that marks the asteroid impact which wiped out the dinosaurs is a timestamp of a sudden, violent cosmic intervention. These geological clocks show us that time's imprint is not just written in the light from distant galaxies, but is embedded in the very ground we walk on, connecting the cataclysm of a supernova to the age of a dinosaur bone, and the pulse of the sun to the age of a pharaoh's tomb. Our own star, the sun, keeps a rhythm of its own. Every 11 years or so, it reaches a peak of turbulent activity, its surface mottled with dark sunspots and erupting with violent solar flares. This is not random chaos, but the pulse of a vast magnetic heartbeat, a cycle driven by the churning dynamo of plasma deep within the sun's core. These solar maximums and minimums are far more than a celestial light show. They directly shape our technological world. Intense solar storms can unleash torrents of charged particles that overwhelm power grids on Earth, causing widespread blackouts. They create dazzling auroras, but they also pose a serious radiation threat to astronauts and can disrupt the delicate electronics and timing signals of satellites in orbit, including those crucial GPS satellites that our atomic clocks rely on. Even the subtle drag exerted by a heated, expanded upper atmosphere during solar maximum can slowly degrade satellite orbits, requiring constant corrections. This 11-year rhythm is itself embedded within a grander cosmic cadence. As our sun orbits the center of the Milky Way, it does not travel a smooth path. It bobs up and down through the galactic plane, a motion that some scientists suspect could modulate its activity over much longer timescales, perhaps influencing the profound cold spells Earth has experienced in its past. We can trace these long-term patterns by looking into history. Ancient Chinese astronomers meticulously recorded sightings of sunspots, their ink on silk providing a data stream that stretches back millennia. In more recent history, from the mid-1600s to the early 1700s, this solar heartbeat nearly stopped. During the period known as the Maunder Minimum, sunspots virtually disappeared for decades. This solar hibernation coincided with the coldest part of the Little Ice Age, a time when frost fairs were held on the frozen River Thames in London. By linking these historical observations of a quiet sun with the climatic records locked in tree rings and ice cores, we can calibrate the sun's long-term clock and understand its influence on our planet's environment. The sun, therefore, is our local laboratory for stellar time. By studying its cycles, we learn how stars of all types mature and change, how their magnetic personalities evolve over billions of years, and how they ultimately mark the passage of time on a cosmic scale. This journey from our local star's rhythm naturally expands our view to encompass the entire galaxy, a swirling disk of 100 billion stars, each with its own time to tell. Our solar system is not a static island in space. It is a traveler on a grand, circular voyage. Every 230 million years, we complete a single orbit around the galactic center, a period so vast it has been named the cosmic year. This is the clock of the galaxy, a metronome whose deep, slow tick frames the entire history of life on our planet. The last time we were in this particular position in the Milky Way, the dinosaurs were just beginning their rise to dominance. A single cosmic year encompasses the entire lifespan of a species, the drifting of continents, and the slow transformation of our atmosphere. This galactic rhythm connects the biological drama on Earth to the grand dynamics of the cosmos itself. As we journey around the center, we do not move through empty space. Our spiral galaxy is a structured whirlpool of stars, gas, and dust, and our solar system periodically passes through its denser spiral arms. These passages are not gentle transitions. They are encounters with regions of intense stellar birth and greater gravitational turbulence. Scientists hypothesize that as we move through these arms, the gravitational jostling can disturb the distant cloud of icy bodies at the solar system's edge, the Oort cloud. This disturbance sends a shower of comets spiraling inward, some of which may collide with Earth. There is compelling evidence that mass extinction events in our planet's deep past, like the one that wiped out the dinosaurs, correlate with these spiral arm passages, linking a galactic clock cycle to a terrestrial cataclysm. Our local stellar neighborhood is also constantly shifting. Close encounters with other stars, though rare on human timescales, are inevitable over a cosmic year. A passing star could gravitationally perturb the Oort cloud just as effectively as a spiral arm, triggering a similar comet shower and potentially altering Earth's climate for millennia. By meticulously mapping the motions of millions of stars, astronomers can rewind this galactic film, reconstructing our past encounters and predicting future ones. These stellar motions act like hands on a clock, allowing us to measure when our galaxy merged with smaller dwarf galaxies in the ancient past, events that left stellar streams as evidence of their cosmic time. This scale of timekeeping is almost impossible to fully grasp. It operates on a level where a single tick is longer than the existence of humanity itself. Yet, this immense galactic clock is intimately connected to our own story, its slow rotations having directly influenced the evolution of our planet and the life upon it. Galactic time reminds us that we are part of a dynamic, rotating structure whose rhythms, though imperceptible to our brief lives, set the stage for everything we know. This grand orbital dance is just one movement in a far vaster symphony, one written on the largest canvas imaginable, the structure of the universe itself. Gravity's patient work did not sculpt isolated islands, but a single, sprawling tapestry. On the grandest scales, the universe reveals its architecture as a cosmic web, a vast network of glittering galaxy clusters connected by faint filaments of stars and dark matter, all weaving around immense, empty voids. This is not a random scattering, it is the fossilized record of time itself. The delicate strands and dense knots of this web hold a chronological story, a timeline written not in words, but in the arrangement of matter across billions of light years. Cosmologists become cosmic archaeologists, mapping the positions and motions of millions of galaxies to trace how this intricate structure grew from the nearly smooth, hot soup of the Big Bang. They use powerful telescopes to conduct immense surveys, peering deeper into space and thus further back in time to see the web in its younger, more primitive states. These observations are then fed into colossal computer simulations that replay cosmic history, letting gravity's invisible hand slowly pull matter into the filaments and nodes we observe today. By matching the simulated web to the one we see outside our window, we can calibrate time against the growth of these structures. The timeline they reveal is governed by an unseen struggle. Dark matter's gravity provides the scaffolding, relentlessly pulling matter together to form the web's skeleton. Meanwhile, dark energy acts as a counterforce, its repulsive push accelerating the expansion of space and stretching the cosmic voids ever larger, making it harder for new structures to form. The specific pattern of the web, the thickness of its filaments and the size of its empty bubbles tells us the relative strength of these two titans throughout cosmic history. It is a direct readout of the universe's expansion story. This large-scale perspective shows us that time is not merely something the universe keeps, it is something the universe is built from. The very shape of the cosmos, its grand morphology, is a physical manifestation of eons passing. To understand this architecture is to read a historical narrative where every galaxy cluster is a chapter and every vast, dark void is a pause between epochs, a story of how gravity wrote history on the canvas of space. This irreversible flow from past to future, the arrow of time we all feel, finds its most profound explanation not in gravity or quantum spins, but in a simple, universal tendency toward disorder. The second law of thermodynamics states that entropy, a measure of randomness, always increases in any isolated system. Think of a drop of ink falling into a glass of water. It never spontaneously gathers back into a single, dense droplet. Instead, it spreads out, its molecules dispersing into a uniform, disordered tint. This one-way process from order to disorder is the fundamental clock ticking behind everything we experience. It is why we remember the past but not the future, why a shattered glass does not reassemble itself, and why stars burn out and never reignite. This relentless increase in entropy provides the universe with its most undeniable arrow, pointing irreversibly from a unique past toward an uncertain future. The origin of this arrow lies in the universe's very first moment. The cosmic microwave background reveals a cosmos that was incredibly smooth and uniform, a state of surprisingly low entropy. While this might seem highly ordered, it was actually a state of tremendous potential, like a perfectly still, massive boulder poised at the top of a hill. The universe was wound up, ready to fall into a state of higher disorder. From that initial, finely tuned condition, the only direction to go was down into the complex, structured, but ultimately more disordered universe we see today. Gravity is the master sculptor of this descent into chaos. That initial smooth distribution of matter was unstable. Over eons, gravity magnified the tiniest fluctuations, pulling matter into galaxies, stars, and planets. This seems like it creates order from disorder, but on the grandest scale, it actually increases the overall entropy of the universe. A star is a magnificent, ordered nuclear furnace, but it is also a fantastically efficient engine for spreading energy and increasing disorder. It takes concentrated hydrogen fuel and disperses it as light and heat across the void, a massive increase in entropy that drives the cosmic clock forward. This thermodynamic view connects the smallest quantum events to the largest cosmic structures. At the microscopic level, the random jostling of particles leads to the emergent order we see in life and technology. Your body is a localized pocket of stunning order, but it maintains that order only by consuming energy from the sun and increasing the entropy of your surroundings. You are a whirlpool in a river flowing relentlessly toward disorder, a temporary eddy of structure in the universal current. This profound link between quantum randomness and cosmic evolution suggests that the flow of time itself may be an emergent property, a consequence of the universe's journey from a low entropy past to a high entropy future. It complements the relativistic clocks of black holes and the quantum vibrations of atoms, providing a narrative drive for the entire cosmos. The ticking of any clock, from an atomic fountain to a pulsar's spin, is ultimately powered by this universal tendency toward disorder, marking not just intervals but the irreversible direction of time's arrow itself. This unified timeline of the cosmos is now being written by listening to the universe with more than one sense. Multi-messenger astronomy is the practice of observing a single cosmic event using different types of signals, from the light our eyes see to the ripples in space-time and the ghostly particles called neutrinos. Each of these messengers travels at the speed of light, but they originate from different processes within the cataclysm, and they carry their own unique clocks. When a pair of neutron stars spiraled into each other in 2017, the event was not just seen, it was felt. Gravitational wave observatories recorded the precise chirp of the inspiral, a clean signal that marked the exact moment of merger according to the geometry of spacetime itself. Just 1.7 seconds later, space-based telescopes detected a flash of gamma rays, the electromagnetic echo of the violent collision. This incredible synchronization, this 1.7-second delay, was not an error. It was a revelation. It confirmed that gravitational waves and light do indeed travel at the same speed, a fundamental test of Einstein's theory. More than that, it gave astronomers two perfectly synchronized stopwatches for the same event. The gravitational wave signal provided an independent, highly accurate measure of the distance to the merger. The light from the resulting kilonova allowed them to identify the host galaxy and measure its redshift. By combining these two measurements, scientists created a powerful new way to measure the Hubble constant, the universe's expansion rate, free from many of the uncertainties that plague other methods. This is the power of cross-verification. It is like having two witnesses to a crime, one who saw it happen and one who heard it, their stories aligning to pinpoint the truth with far greater accuracy than either could alone. To make these fleeting observations possible, a global network of observatories must operate in perfect sync. When a gravitational wave detector or a neutrino observatory triggers an alert, telescopes around the world and in space swivel to the coordinates within minutes, their internal atomic clocks synchronized to within microseconds. This coordinated effort creates a single, planet-sized instrument, a chronometer for the cosmos that can capture the birth of a black hole or the shredding of a star by a supermassive gravity well in real time. Each type of messenger fills in a part of the story that the others miss. Cosmic rays, which are high-energy atomic nuclei, point back to their violent origins. Neutrinos, which barely interact with matter, escape directly from the heart of an exploding star, bringing a timestamp from the very core of the explosion. By weaving these disparate threads together, multi-messenger astronomy does not just observe events. It reconstructs their entire history with a fidelity that was once unimaginable. This is the pinnacle of integrated timekeeping, a symphony of signals where the rhythm of space-time aligns with the flash of light and the whisper of a particle to tell a complete story. It is a preview of a new era in astronomy, one where every cosmic clock, from the atomic to the astrophysical, ticks in concert to reveal a deeper layer of reality. The next generation of cosmic clocks is already taking shape, not in laboratories on Earth, but in the blueprints for observatories in the void. The European Space Agency's ATHENA, an X-ray observatory, will stare into the hearts of galaxy clusters heated to millions of degrees, tracing how dark energy has sculpted the universe over billions of years. Alongside it, NASA's Nancy Grace Roman Space Telescope will map the cosmos in infrared light, capturing the faint echoes of supernova to measure the expansion history with a precision we can only dream of today. These are not just telescopes, they are time machines calibrated by the most advanced atomic clocks ever sent into space. Their mission is to resolve the lingering tension in the Hubble constant, to pin down the true tempo of the universe's expansion, and finally understand the nature of dark energy. But the ambition goes beyond observation. Concepts are being drafted for quantum sensors that could operate in the pristine quiet of the lunar surface, far from Earth's seismic murmurs and radio noise. A network of atomic clocks on the Moon would create a stable timekeeping base for the entire solar system, a foundational grid for a future interplanetary internet. These off-world chronometers would allow spacecraft to navigate with absolute autonomy, calculating their position by exchanging time signals with the lunar network, eliminating the long delays of communicating with Earth. This is the practical application of cosmic time, the framework for a civilization that moves between worlds, yet the scientific promise is even more profound. Placing these exquisitely sensitive clocks in different gravitational environments, like on the Moon and in deep space, provides a perfect laboratory for testing relativity. Could we detect a subtle anomaly in how time dilates near a large planet like Jupiter? might we find evidence that the fundamental constants, which we assume are unchanging, actually vary slightly across the vastness of space? Any such deviation would be a seismic event in physics, pointing toward new laws and a deeper layer of reality. The future of cosmology is the integration of quantum technologies with our view of the stars, using the tiny, precise vibrations of atoms to measure the grandest motions of the cosmos. This relentless pursuit of a perfect clock, however, nudges us toward a profound ethical frontier. As we learn to measure time with ever greater fidelity, we edge closer to the theoretical possibility of influencing its flow. While the manipulation of cosmic time remains firmly in the realm of science fiction, the very act of defining it so precisely forces us to consider our responsibility. If time is the substrate upon which all existence is written, what does it mean for us to now hold the pen that charts its deepest rhythms? This mastery over time's measurement places a profound responsibility in our hands. The same atomic precision that guides a rover on Mars can also guide a missile to its target with terrifying accuracy. High-frequency trading algorithms, synchronized to nanosecond scales, can trigger market flash crashes in the blink of an eye, concentrating wealth and power through temporal advantage. As we extend this control beyond Earth, we must confront a new frontier of equity. Will access to a solar system-wide time network be a universal good or a privileged resource? A civilization with the ability to synchronize fleets across the void holds an unimaginable advantage over one confined to a single planet's relativistic frame. This could create a temporal divide, a new kind of inequality not of wealth or location, but of time itself, echoing historical conflicts where control over calendars and clocks was a tool of power. Philosophically, our precise knowledge of the cosmos's 13.8 billion-year lifespan can be both humbling and disorienting. We now know our entire history is less than a heartbeat in the life of the universe, and that all we have built will one day be erased in a cold, dark finale. This cosmic perspective forces a radical re-evaluation of human purpose. If our time is so fleeting, what is the meaning of our struggles, our art, our love? This tension has already seeped into our culture, from the existential dread in some modern art to the rise of secular philosophies that seek purpose not in eternity, but in the significance of our brief moment in the sun. Our relationship with time has always shaped religion and spirituality, from cycles of reincarnation to linear paths to salvation. Now, with a definitive cosmic timeline, we are compelled to find meaning within its fixed borders, to create our own light against the backdrop of an indifferent clock. This journey reveals that every clock we build is more than a machine. It is a mirror reflecting our deepest values, our fears, and our aspirations. The ultimate challenge is not whether we can build a perfect clock, but whether we can wield its power with wisdom, ensuring that our synchronization with the cosmos leads not to division, but to a deeper, more humane connection across the vast expanse of time. Our mastery over time now extends into the digital frontier, where we are no longer just observers of the cosmic clock, but its architects. Within virtual realities and complex simulations, time becomes a programmable variable. We can slow it to a crawl, speed it to a blur, or even rewind its flow with a simple command. These digital worlds operate on their own encoded chronology, a stark contrast to the relentless, one-way march of time we experience in our physical reality. This ability to manipulate time challenges a fundamental assumption that our perception of cosmic time is absolute. It raises a provocative question: if we can create simulated universes with arbitrary time flows, could our own reality be a kind of simulation, running on a substrate of unknown physics with its own master clock? This is not just a philosophical thought experiment. It is a practical tool driving modern cosmology. scientists build immense computer models that simulate cosmic evolution from the first picoseconds after the Big Bang to the formation of vast galaxy clusters. These are digital cosmic clocks of incredible sophistication. Inside a supercomputer, processes that would take billions of years in the real universe unfold over mere months or weeks. Researchers can watch a virtual galaxy spin through its entire life cycle, observing how dark matter halos coalesce and how spiral arms emerge from the gravitational dance. This compressed timeline is not just a convenience, it is a powerful experimental platform. It allows cosmologists to test theories by running the simulation over and over, tweaking the initial conditions each time to see which version of virtual reality best matches the actual universe we observe outside our window. The most profound experiments involve altering the very laws of physics within the simulation. What happens to the flow of time if the strength of gravity is doubled? How does galaxy formation change if the cosmological constant, which governs dark energy, is set to zero? By creating multitudes of these alternative universes, each with its own unique set of physical constants, we gain deep insights into the fine-tuning of our own cosmos. We can explore how time itself might operate in realities where the fundamental forces are balanced differently, revealing whether our experience of a consistent, linear time is a universal truth or a local accident. This digital approach blurs the line between reality and simulation, not in the sense that our world is fake, but in the realization that the mathematical laws we use to describe the cosmos are the same ones that power these virtual realms. The same code that simulates the birth of a star can render a photorealistic landscape in a video game. This intersection of computing and cosmology suggests that information and computation may be as fundamental to the universe as space and time. As we explore these digital frontiers, we see a reflection of the same interconnectedness found in all cosmic timekeepers, from the ticking of an atom to the spin of a galaxy. Our quest to build a perfect clock has led us to create entire digital universes, and in their evolving codes, we are reading a new chapter in the ancient story of time. This grand synthesis is already underway, a quiet revolution in how we define time for an interplanetary species. The International Astronomical Union, the global authority for celestial naming and standards, is not just mapping the stars but also forging a consensus on time itself. They have established nuanced time scales like terrestrial time, which is locked to the ticking of atomic clocks on Earth's surface, and barycentric dynamical time, which is the master clock for the solar system, centered on the common center of mass of the Sun and planets. This shift from a terrestrial to a solar system perspective is fundamental. It means calculating the precise time delay for a signal traveling from Earth to a rover on Mars is no longer an approximation, but a standard, calculable part of the protocol. Future missions will carry their own ultra-precise clocks, and their onboard computers will constantly translate between their local Martian time and this solar system standard, ensuring that a command sent from Houston arrives at the exact nanosecond intended, despite the minutes of light travel delay. This intricate dance is the only way to coordinate a fleet of robotic explorers across the vast, silent gulf between worlds. The ambition extends even further to the silent metronomes of deep space. Pulsar timing arrays use networks of these spinning neutron stars as a natural galactic positioning system. By monitoring the arrival times of pulses from multiple pulsars scattered across the sky, scientists can detect the slight variations that indicate our position and motion within the galaxy. This celestial GPS does not rely on any human-made clock, but on the immutable rhythms of the cosmos itself. The goal is to weave these disparate threads, the quantum tick of atomic clocks, the relativistic gravity of dynamical time, and the steady beat of pulsars, into a single, resilient fabric of cosmic time. This is not merely a technical challenge, it is a profound exercise in theoretical physics. Every calculation must account for the time dilation caused by the sun's gravity, the velocity of a spacecraft, and even the subtle drag of our galaxy's dark matter halo. A clock in orbit around Jupiter experiences a different flow of time than one on a probe headed for the icy Kuiper belt. A universal standard cannot force them to tick in unison that would violate the core principles of relativity. Instead, it provides a common language, a set of equations that allows every clock to know its precise relationship to every other, creating a fluid, dynamic map of time across the expanding void. The success of this endeavor hinges on unprecedented international cooperation. We cannot afford a future where competing nations or corporations operate on conflicting time standards, creating a chaotic cacophony of temporal protocols that would jeopardize missions and make space a dangerous place. The establishment of a unified cosmic time would be a milestone for civilization, a testament to our ability to rise above terrestrial divisions and collaborate on a truly cosmic scale. It represents the ultimate harmonization with the universe's rhythms, a silent agreement written in mathematics and confirmed by the stars that we are ready to step into the cosmos not as isolated visitors, but as a synchronized whole. Our lives are a fleeting spark against the deep, dark ocean of cosmic time. We measure our years in decades while the stars above burn for billions. This profound mismatch between our brief existence and the universe's immense age can feel overwhelming, yet it is our unique human consciousness that allows us to even contemplate such scales. This awareness is a powerful engine. It drives the scientist to point a telescope at a galaxy whose light is older than our planet. It moves the artist to paint the slow dance of nebulae or the composer to write a symphony for the cosmos. It fuels the spiritual seeker looking for a connection to something eternal. Our mortality is the very thing that propels us to seek meaning in the vast, impersonal clockwork of the universe. We find ways to bridge this gap in our daily lives. The simple act of stepping outside on a clear night and looking up is a form of time travel, connecting your present moment with light that has been journeying for millennia. The practice of mindfulness, of being fully present, is another way to touch eternity, to find a deep and personal rhythm within the frantic pace of modern life. Astronomy education plants seeds of cosmic perspective, helping new generations understand their place in a story 13.8 billion years long. Our fleeting experience of time is not just a limitation, it is the gift that makes our exploration meaningful. It is the reason we send probes to other worlds, preserve our history, and strive to leave a mark, however small, on the fabric of reality. We are the universe's way of knowing itself, and our brief, brilliant moment of awareness allows us to read its history and imagine its future, enriching our journey through space and time with purpose and wonder. Our journey through the cosmic clocks has revealed a universe intricately woven with time. From the frantic quantum vibrations inside an atom to the majestic, slow spin of our galaxy, every scale of existence contributes its own rhythm to a single, coherent narrative. We have traced humanity's own path, from the ancient sky watchers who first read the time in the stars to the builders of quantum sensors that listen to the whisper of spacetime itself. Each leap in our understanding has not distanced us from the cosmos, but has instead woven our own story more deeply into its fabric. The day the universe learned to keep time was not a singular event in the distant past. It is an ongoing story, one that continues with every new discovery, every more precise clock we build, and every deeper question we ask. This grand exploration challenges us to constantly refine our tools and expand our horizons, reminding us that time is far more than a simple measure. It is a fundamental essence of existence, the very stage upon which the cosmos performs its epic. I would love to hear which of these cosmic clocks captivated you the most. Share your thoughts on these wonders in the comments below, and if you enjoyed this journey, subscribe for more explorations into the mysteries of space. In the vast, expanding expanse of the cosmos, remember that every single moment is a precious, irreplaceable tick in the grand clock of the universe.